NASA's James Webb Space Telescope has hardly opened its eyes, and the universe is new.
In the silent dark beyond the sun, Neptune has always been a frozen world of calm blue clouds. But one night, that calm was broken. A sudden burst of heat erupted from the planet's southern sky, glowing brighter than anything ever seen before. The James Webb Space Telescope caught it by accident, a flash so powerful it looked like the planet had caught fire. For a world that sits 30 times farther from the sun than Earth, nothing about that should be possible. So what could make the coldest planet in our solar system burn in a matter of seconds? At first, the James Webb Space Telescope was not even looking for anything unusual. It was running a routine scan of Neptune's southern hemisphere, collecting data on the planet's clouds, magnetic field, and faint weather patterns. But then, out of the quiet blue, came something that made every scientist stop breathing. A flash of infrared light burst across Webb's sensors, so intense that for a moment the entire hemisphere seemed to glow. Infrared light means heat, and Neptune is supposed to be cold. Its atmosphere usually rests at about -350 degrees Fahrenheit. That is why the sudden rise in temperature made no sense. The heat spike appeared in a single, concentrated spot, surrounded by perfectly normal cold zones. It was not spread evenly, which ruled out any kind of internal storm or chemical reaction. Instead, it looked like a massive pulse of energy had entered from outside the planet, like something had struck it at incredible speed. Scientists quickly checked for instrument errors, but the readings were solid. The same pattern appeared in multiple exposures, each confirming the strange heat signature. Soon after, Neptune's upper clouds began to twist and ripple, forming strange arcs that stretched for thousands of miles. Those waves were not random. They followed a circular path, spreading outward from the same location as the heat flare, just like ripples from a stone dropped into water. It was the first visual clue that something physical had happened, something powerful enough to shake the planet's atmosphere. Even more shocking was what appeared above the clouds. A thin haze formed in the upper layers, shimmering faintly in both infrared and visible light. Spectral readings revealed unusual gases compounds that do not normally exist there. They were short-lived, forming and disappearing within hours, which suggested a violent chemical disturbance. That haze could have been the residue of vaporized material from the impact itself, or from gases released deep within Neptune's layers by the force of the collision. As more data came in, scientists began comparing Neptune's light curve over the next several days. The affected area stays hot longer than expected, its brightness slowly fading rather than vanishing instantly. That lingering glow indicated that massive energy had been injected into the planet's atmosphere and was now radiating away. For Neptune, which takes 165 years to orbit the Sun, this was like a heartbeat, a short, sharp pulse in the middle of eternity. When the news reached Earth, observatories around the world scrambled to confirm what Webb had seen. Hubble, the European Southern Observatory, and telescopes in Hawaii turned their focus toward Neptune. They too detected faint traces of the haze and subtle shifts in the planet's light spectrum. What Webb had caught was real. A silent giant had just been struck by something from the dark. But the question no one could yet answer was this: what exactly hit Neptune, and how could an object travel that far only to collide with a planet so remote? When scientists studied the data closer, they found patterns that no storm or internal activity could explain. The layers of heat were stacked one over another like ripples frozen in midair, showing how something powerful had slammed into Neptune's atmosphere. It was not a natural updraft, not a jet of gas rising from below. It was energy forced inward from an outside source, and that changed everything. The readings pointed to an impact something large enough to punch through the upper clouds and dump a massive amount of energy inside. Simulations showed that the heat wave spread outward in a perfect circle, consistent with what happens when an object strikes at high velocity. The spot of impact became the brightest point on the planet, glowing in infrared for hours before slowly fading. For Neptune, a world of calm blue ice, it was like a wound that refused to close. But what kind of object could hit a planet 30 times farther from the Sun than Earth? There are no nearby asteroids large enough to make it that far, and comets usually break apart before reaching Neptune's orbit. The best estimate came from the spectral data and energy measurements. It suggested the intruder was between 30 and 50 kilometers wide, about the size of a city, and composed of volatile ices mixed with rocky material. That made it similar to a trans-Neptunian object, one of the icy bodies orbiting beyond the planet in the Kuiper Belt. Sometimes, gravitational tugs from Neptune or passing stars can knock one of these objects off course, turning it into a wandering projectile. Astronomers believe that is what happened here. A rogue Kuiper Belt object thrown out of its orbit millions of years ago may have slowly drifted until Neptune's gravity pulled it in. Once it crossed the planet's path, there was no escape. The collision would have released energy equivalent to hundreds of millions of megatons of TNT, enough to shake even a gas giant. The shockwaves that followed would explain the disturbed rings, the displaced clouds, and the sudden haze that wrapped around the southern hemisphere. However, not everyone agreed on that theory. Some researchers pointed out that the trajectory and timing of the impact seemed too perfect. They questioned how an object could travel undetected across such a vast distance without being spotted earlier. A few suggested that the impactor might not belong to our solar system at all. If it came from interstellar space, it could have entered the system at high speed, bypassing the Sun's pull and heading straight toward Neptune. That idea sounded extreme, yet the physics fit surprisingly well. If true, it would mean that something from another star had just made contact with one of our planets. And if such an object could strike Neptune, what would stop another from moving closer, perhaps toward us? When the object finally struck, Neptune reacted like a living giant waking from a deep sleep. Shockwaves spread across its southern hemisphere, rolling through the planet's upper atmosphere with unimaginable power. In just minutes, the calm blue clouds that had surrounded the planet for centuries twisted into violent spirals. The impact zone glowed like a scar, radiating energy that raced outward in waves. Scientists observed the planet's weather system as it began to change shape. Jet streams that normally flowed in smooth bands suddenly accelerated, bending and colliding as if the planet itself had been jolted from within. The powerful winds, among the fastest in the solar system, reached even higher speeds, tearing apart cloud structures that had once seemed permanent. From Earth's perspective, Neptune's serene appearance vanished, replaced by a shifting world filled with turbulence. For the first time in decades, the planet looked alive, but the changes went far beyond its clouds. Deep inside Neptune, something was stirring. Its magnetic field, already tilted and unstable, began to fluctuate wildly. Instruments detected sudden shifts in particle flow, suggesting that the planet's internal currents had been disturbed. This was not just an atmospheric event, it was planetary. The collision had shaken Neptune's magnetic heart, possibly reaching down to its molten interior where electric storms generate its magnetic field. For a brief moment, Neptune's magnetic signature pulsed differently, as if it had skipped a beat. The impact also reached the rings that circle the planet. Normally faint and almost invisible, these thin arcs suddenly brightened. Dust and ice particles reflected sunlight more intensely, hinting that the collision had kicked new material into orbit. Astronomers recorded the flicker of those rings for several days before they slowly dimmed again. It was as though the planet had been surrounded by a halo of debris, an echo of the impact that refused to fade. Even the planet's color shifted subtly. Spectral imaging revealed variations in the blue tones, caused by changes in methane levels within the atmosphere. That might seem like a small detail, but for Neptune, whose hue depends on delicate chemical balances, it was proof that the impact had rewritten its climate. Every layer, from the outer winds to the deep magnetic field, had been touched by the force of that single strike. To the scientific community, this was more than a celestial accident. It was a window into how planets respond to violence. If such an event could alter the magnetic rhythm of a gas giant, what would it do to a rocky world like ours? Neptune's reaction showed that planets are not passive. They absorb, react, and evolve after every cosmic blow. The question now was no longer just what hit Neptune, but how far the effects of that collision might reach across the solar system. The real mystery began after the dust settled. When astronomers looked at Neptune's atmosphere in the days following the impact, they noticed something that didn't belong there. The chemical fingerprints had changed. New gases were rising through the atmosphere, molecules that had never been detected on Neptune before. Spectral scans revealed strange hydrocarbons and nitrogen compounds forming in the upper layers. Some of them, like ethane and acetylene, are usually found in comets or the atmospheres of Titan and Pluto, not on Neptune. They appeared suddenly, in quantities too large to be explained by normal chemistry. It was as if the planet's own elements had been shaken up, forced to combine in ways they never had before. For scientists, this was a chemical alarm bell, proof that the collision had altered the planet's balance at a molecular level. One explanation was that the impactor had brought those compounds with it. If the object came from the Kuiper Belt, it could have carried frozen ices of methane, nitrogen, and complex organic material. The heat of the collision would have vaporized these substances, spreading them like invisible dust across the upper atmosphere. That would explain the temporary haze observed after the strike, a fog of foreign particles mixing with Neptune's natural gases. But another theory went even deeper. Some researchers proposed that the immense heat from the impact triggered new reactions within Neptune's atmosphere itself. Methane, which gives the planet its blue color, might have broken apart under the energy shock, forming chains of more complex hydrocarbons. These reactions could have briefly transformed Neptune into a vast chemical laboratory where pressure and temperature combine to create compounds never seen before in our solar system. To planetary scientists, this was priceless. It offered a rare glimpse into what might happen inside gas giants under extreme conditions. The aftermath also gave insight into how energy travels through an atmosphere. The warm gases created by the impact did not just vanish, they moved, spreading around the planet in slow, invisible waves. For weeks, instruments picked up temperature fluctuations that hinted at chemical mixing across the globe. It was like watching the planet breathe, trying to regain balance after being struck. If these compounds truly came from outside Neptune, It would mean the collision didn't just release energy, it changed the planet's chemistry forever. Even a slight shift in molecular composition can affect temperature, color, and weather patterns for centuries. That means Neptune might not fully return to what it was before the event. Its skies, its winds, even its magnetic behavior may now carry traces of that one foreign visitor. To scientists on Earth, the implications went far beyond Neptune. If a single impact could alter a gas giant's chemistry, could the same happen elsewhere? Could a similar strike on another planet, or even on Earth, introduce new elements, perhaps even the building blocks of life itself? That question would soon become the center of a much larger debate. For centuries, astronomers believed the outer solar system was frozen in silence. Beyond Neptune lay a realm thought to be calm, predictable, and almost lifeless, a cosmic graveyard where time itself seemed to stop. But the collision changed everything. It proved that the solar system is not static, but still alive, still shifting, still rewriting its own story. In the wake of the impact, scientists began to question long-held models about how planets evolve. If a massive strike could happen in the 21st century, then the outer planets were not relics of the past. They were still part of an active, dynamic system. Data from Webb showed evidence of energy redistribution across Neptune's atmosphere, a clear sign that its internal circulation was reacting. The shockwaves may have traveled deeper than expected, stirring layers that had remained undisturbed for billions of years. This discovery forced scientists to revisit an uncomfortable question: how many more such collisions are still happening, unnoticed in the darkness beyond Pluto? The idea that the solar system remains active is both thrilling and unsettling. It suggests that space is not a peaceful neighborhood, but a chaotic arena where planets continue to face cosmic impacts. Even now, billions of rocks, ices, and fragments orbit the Sun on unpredictable paths. They revealed the cost of living under relentless scrutiny and the ways Michael tried to create safety in a life that no longer felt his own. Each one of those could become the next projectile, a silent traveler that might one day hit another world. To understand what this means, scientists compared Neptune's event to past cosmic collisions. Jupiter's scars from the Shoemaker-Levy 9 impact in 1994 offered one precedent. That event reshaped how we saw the outer planets, showing they could still experience devastating strikes. Now, Neptune had joined that list, proving that even the most distant worlds are still targets in a living, breathing system. In a way, the solar system behaves like an ecosystem, constantly changing, exchanging energy, and never truly stable. This revelation also changes how we look at planetary formation itself. The processes that shaped Earth billions of years ago may still be occurring on the outskirts of our cosmic home. Every collision redistributes mass and momentum, subtly influencing the orbits of nearby objects. It means that even in its so-called quiet era, the solar system continues to evolve. The same forces that once built the planets are still at work today, hidden in the cold shadows where few telescopes can see. For astronomers, this realization is humbling. It reminds us that the solar system is not a museum of ancient objects. It is a living network, moving and reacting to forces we barely understand. The impact on Neptune is only one chapter in an ongoing story of motion and chaos that began 4.5 billion years ago. And if the outer planets are still colliding, still shifting, still sending shockwaves through space, what might that say about our own planet's future in this restless cosmic system? The deeper scientists looked into the data, the clearer it became that Neptune's collision was more than a random event. It was a wake-up call, a reminder that the solar system is still alive, still unpredictable, and still dangerous. For decades, astronomers had believed that the era of major impacts was long over, but this single strike proved that the forces that once shaped the planets are still at work today. To understand why, we have to look at the solar system as a living system, not a finished one. Every planet, moon, and asteroid pulls on each other, locked in a slow gravitational dance. Over millions of years, even small tugs can change an orbit, pushing one object closer to another. That means collisions are not rare accidents. They are part of the system's natural evolution. Neptune's impact was not the exception. It was proof that our cosmic neighborhood is still moving and reshaping itself. What makes this discovery even more remarkable is that Neptune sits near the outer boundary of the Sun's influence. It is a world on the edge, where sunlight is weak and gravitational control begins to fade. Beyond Neptune lies the Kuiper Belt, a vast region filled with icy debris and wandering objects. Many of these bodies are leftovers from the solar system's birth, untouched since the beginning. Yet even there, chaos reigns. Gravitational nudges from Neptune or passing stars can send these frozen relics spinning inward, turning them into cosmic missiles. Neptune's collision might be one of many signs that the solar system is still active far beyond what we can see. Each impact stirs up energy, shifts magnetic fields, and reshapes the delicate balance between worlds. The idea that planets can still influence one another after billions of years changes how we view our place in the system. It means that no planet, not even Earth, exists in perfect isolation. Every movement in the outer dark could one day ripple inward, affecting the orbits, climates, or even the stability of inner worlds. This new perspective has inspired scientists to rethink what stability really means. Rather than a calm and finished structure, the solar system may be a constantly adapting organism, an interconnected web of motion and change. The discovery on Neptune shows that this web is still vibrating, still responsive, still alive. And if it's alive, then it can evolve. Energy from impacts, gravity, and chemical exchange may slowly shape the next era of our planetary neighborhood. In a strange way, the collision on Neptune serves as both a warning and a reassurance. It tells us that the solar system has not gone silent. It still breathes, still reacts to the universe around it. But it also reminds us that we are part of that same living system. We share its rhythms, its risks, and its future. And if the outer planets are still stirring, sending echoes through the void, how long will it be before one of those echoes reaches Earth? When the shock of Neptune's collision reached Earth, it was more than an astronomical headline. It was a warning. If such a massive event could happen to a planet at the edge of the solar system, then no world was truly safe, not even ours. For years, the idea of a catastrophic impact on Earth had lived mostly in movies and history books, tied to the extinction of dinosaurs or hypothetical end-of-world theories. But now, scientists had real proof that space remains unpredictable, and the next collision might not give any warning at all. The energy released on Neptune was estimated to equal hundreds of millions of megatons of TNT. If an object even a fraction that size struck Earth, it would devastate the planet. A 10-kilometer-wide asteroid would generate enough heat to ignite global fires, darken the skies for years, and cause a collapse of ecosystems. For reference, the impact that wiped out the dinosaurs 66 million years ago was roughly that size. Neptune's event reminded scientists how little control humanity has over the cosmos and how thin the line is between stability and chaos. The unsettling part was how the impact went unnoticed until it had already happened. JWST detected it by coincidence, during an unrelated atmospheric observation. No early alert, no inbound detection, no trace of the object before impact. That realization shocked the scientific community. If an event of such magnitude could escape all radar and telescope systems, it exposed a flaw in our planetary defense efforts. Most telescopes are focused on inner space, tracking objects that threaten Earth directly. But the outer solar system remains largely unmonitored, a blind zone where unknown objects can move freely for decades. In response, several space agencies began to reconsider how they watch the skies. NASA's Planetary Defense Coordination Office, which tracks potentially hazardous asteroids, started studying whether JWST's deep field sensitivity could help identify distant threats. The European Space Agency accelerated work on its Fly-Eye telescope network designed to spot smaller, fast-moving bodies before they get close. Still, even with new technology, experts admit the system is far from perfect. Detecting an object depends on sunlight reflecting off it, and many interstellar rocks or icy bodies are too dark to see until it's too late. That means Earth's first sign of danger might still come from an unexpected flash, just like Neptune's. This event also reshaped how scientists think about planetary survival. It is no longer a question of if a collision will happen again, but when. While the odds of a catastrophic strike in our lifetime are low, smaller impacts occur regularly. Earth's atmosphere protects us from most of them, burning incoming debris before it reaches the ground. But the gap between a harmless meteor and a world-ending asteroid is frighteningly small. The impact on Neptune showed that even a planet with immense gravity and thick gas layers couldn't absorb such energy without long-term consequences. Earth, with its thin atmosphere and fragile ecosystems, would fare far worse. For now, the best defense humanity has is awareness. Every observation, every new telescope, and every mission aimed at studying asteroids is a step toward protecting our planet. But the universe does not wait for us to be ready. Neptune's collision was a cosmic reminder that nature plays by its own rules, indifferent to human timelines or technology. It has already happened once on the far edge of the solar system, so the question is not whether it can happen here, but whether we will see it coming in time. The collision on Neptune was more than a scientific discovery. It was a message from the universe. It reminded humanity that even in the farthest corners of the solar system, chaos still breathes, and nothing is ever truly still. For centuries, we looked at the stars thinking they were eternal, but Neptune's flash proved that creation and destruction never stopped. Every planet, every orbit, every grain of dust still plays its part in this endless cosmic dance. Perhaps the universe is not fading into silence, but preparing for its next movement, one that we may soon witness ourselves. So what do you think? Was this just an accident of nature, or the first warning of something far greater still to come? Don't forget to like, share, and subscribe for more stories hidden among the stars.